Okay. I'm Alan Samuels from SanDisk, and I'm here to talk about optimizing Ceph for all-flash architectures. So just a quick review for those of you that might not be too familiar with Ceph, or you've heard the name but don't really know what it is or what it does. It's a distributed, clustered, sometimes called scale-out storage system. It's an open source project that's available in a lot of environments, and it's heavily used in the OpenStack world. In fact, if you go back and look at the user survey at the end of last year, Ceph is the most deployed storage platform in the OpenStack environment. It supports both object and block interface, and it has a file system interface that's going to be available real soon now. In fact, it's there, but they don't recommend it for production, but they're madly at work on fixing that, and I expect that to go production ready here soon. So it's as I said, it's an open source project. It's been in the Linux kernel for quite some time, since the 2.6 era, and it's about a 10-year-old project, very mature, enterprise deployed in literally thousands of sites, and some of the largest deployments are in the multi-petabyte range. Quick list of the features here. The block storage subsystem has all the enterprise data management features that you're used to, snapshots, clones, it does striping, and also supports incremental backups. The object storage supports both the Swift and the S3 interface, very feature complete, all the way to geo-replication across multiple regions. So the SanDisk first started working with Ceph almost 2 years ago, and we took it out of the box, put it up on Flash. The first thing that we noticed was it just simply didn't run very fast. You couldn't get a single OSD, which is a component of Ceph, to run past about 20,000 IOPS. And that turns out to be important because generally you deploy one OSD for each blob of storage, an SSD, and most SSDs today are running pretty close to 100,000 IOPS. So addressing that performance gap was a big item for us to deal with. Other issues that we looked into was that unfairness in terms of you had multiple clients making requests of the storage system. You want those requests to be handled in a fair way. We would see that there would be periods of unfairness in Ceph, and pretty large excursions in the I/O latencies, which is pretty undesirable. So we dug under the hood and looked into that, and mostly what we found was just not enough parallelism internally in the implementation. Just lots of queues and threads, a lot of single-threaded things around locks, lots of extra context switches, not enough internal caching. There were things that were just being recomputed time and time again that could easily be cached. Off-the-shelf memory allocator had a surprisingly large impact on things like the latency excursions that we were seeing. The built-in allocators in the libraries just did a very poor performance. Simple handling of the network was just not very efficient. There was very high overhead for moving data between the nodes in the distributed system. And some minor things like Nagel's algorithm, for any of you network heads out there, wasn't being properly disabled. So we dug into the code, got rid of the extra queues, sharded the locks, increased the parallelism, added some caching for file handles and things like that, changed the memory allocator, fixed up the network handling. And all of that code, it's an open source project that was all contributed back. Most of the patches are in the Giant release. There's a couple that are streamed out in the Hammer release, which is what's the most currently worked on. And there are components of Ceph in the Linux kernel, the KRBD element. And that's also been contributed. It's not out in any of the specific releases yet. And the most important thing is that all the changes and the performance improvements that we made were fully backward compatible with Ceph. There's no changes in the disk structures, no changes in the wire format. You can just basically take the new code and boot it up and you're ready to go. So results. So here's some graphs that we've got. I'm sorry I'm a little colorblind, but I think the blue, the Firefly numbers, those are the numbers that were in the off-the-shelf before we got started on this project. And you can see that both the delivered performance in terms of IOPS, the graphs on the left, are pretty anemic compared to what we've got with the Giant release, which has our performance optimizations. In fact, in many situations, you're seeing a factor of 10 increase in the throughput through Ceph just from the software optimizations running on the same hardware on Flash. Running on HDD, you won't see any difference because of the speed limiters of HDD. You're not going anywhere fast enough. Just to give you a baseline here, you're seeing 200+ thousand IOPS out of a single 2-socket server. As well as IOPS improvements, dramatic improvements in the latency, both in terms of the variance and just the absolute values. You're seeing in some cases factors of 2 and 3 reduction in the latency for an individual transaction. And though this graph doesn't show it, a dramatic reduction in the variance. That previous graph was for small blocks. For large blocks, the results are even more. You're seeing 12 to 15x in some cases at high queue depths on the bandwidth. We're actually able to saturate the hardware. We were running this on a box that would deliver close to 9 gigabytes a second through a server, and we had no trouble saturating that. But just regular IOs isn't the whole story. One of the things is that as a scale-out system, you have to be able to deal with hardware failures that come and rebuild lost data, either due to outages or actual hardware crashes. And the standard Ceph is optimized for hard drives. It has an interesting algorithm that's sort of looks a lot like rsync that reduces the amount of data that has to be rebuilt. The off-the-shelf standard recovery algorithms are not nearly good on Flash, but it turns out here there wasn't really any code changes that were required, just some configuration changes. I showed those on the previous slide. But this is an example of what we've got. Here we have a system with 30 terabytes of user data. It's been replicated 3 times, so there's 90 terabytes of user data. Into a system with 384 terabytes total data. And we basically yanked out one of the SSDs. So you lost 1/48 of your storage. So that's not quite 2 terabytes. And this is the performance of the system while it's rebuilding the data. So the red line is what you get with the default. And here we're measuring the performance as viewed through normal operations on the front end using the FIO product to measure the performance. You can see that the performance instantly drops off dramatically and stays quite low for about 40 minutes in this case. And then it picks up to still disappointing, about 80% of the peak throughput. And that continues on for about another hour. And then finally, it resumes normal operations. Okay. Whereas with the settings I showed you on the previous slide, which is, I guess that's a gray line. What you can see there is the performance is pretty much unaffected all the way through the rebuild operation. And that just really translates into a much tighter relationship between your delivered performance and the demands. You don't have to over-provision your infrastructure nearly as much to deal with these kind of operations. And that's basically all I have. Are there any questions? Okay, well, thank you very much. Whoops. We have a late question.
Did you do any optimizations with maybe atomic operations that Flash supports, or trim, or anything like that?
So the question was whether we had done anything with Flash-specific operations like trim or atomic. And the answer is, in the current releases, no. We haven't taken advantage of that. We're continuing to dig into Ceph. We have a lot of interesting stuff that's in the pipeline yet that I'd love to talk about, some of which includes some of the things that you're talking about. So you can expect to see more performance coming out of that code base here in the future. Yes?
Do you do anything special with the journal since you're already Flash?
So the question is whether we did anything special with the journal because we're already on Flash, and the answer is no. Okay. Again, with the numbers that you saw. Changing the way journaling is done is something that we're actively working on. There's, once you're in an all-Flash system, the way that the off-the-shelf code handles the journal is far from optimal on an all-Flash system, and we're very much digging into that. Are there any more questions? Okay, I think we're done again.